Alright, welcome to Academic Daddy's class. So you can see very well, I said use Norton's theorem to find the current in the 10 ohm resistor. The 10 ohm resistor is this. This is the 10 ohm resistor. So if this is the 10 ohm resistor and we are to use Norton's law, so what it simply means is that whenever you hear Norton's theorem, the principal idea is to simply make use of nodal analysis. Make use of nodal analysis when they ask you to use Norton's theorem. So the only difference is just that since they are talking about 10 ohm resistor here and we are to use Norton's theorem, I will short circuit this 10 ohm resistor so that instead of having this 10 ohm here, this resistor will leave, and if I'm short circuiting it, this becomes just wire running straight. So once you put this in order, you've obeyed Norton's theorem. So the next thing is to apply nodal analysis, and nodal analysis simply talks about finding the junctions or the nodes. So what are the nodes from this end to this point? See, let me analyze it. So this is a resistor, a 4 ohm resistor. This is wire. This wire runs through to the next resistor, and this wire runs again. This wire runs again, come this way, and then when this wire come down to this point, watch. As this wire come down to this point, this wire now continues. So once you see a resistor, it stops, but because the wire continues, it doesn't meet any other resistor. It goes around and then comes back to the voltage. The minute you meet a voltage, you stop, but you know that a voltage is connected with wire, so it comes back. This continues as well on the down part, goes again, you meet a voltage, the negative and the positive, then you stop. So it simply means that what this particular circuit has, removing that 10 ohm resistor, is just a node. So if that is the truth, that means I'll call this V1, call this V1, call this V1, this is V1, V1 and V1. So it has just one node. So we have 10 voltage here, we have 12 voltage on this end, and this is the 4 ohm resistor, and this is the 6 ohm resistor. So if you know that, it simply means that if I look at this very well critically, you see that V1 to V1 is the same, and we have this rule in nodal analysis that whatever voltage I have, that voltage is flow from higher potential, current flows from higher potential, that is higher voltage to lower voltage. So if I know that, it simply means that looking at this voltage, we have positive and negative. Current enters through the positive and leaves through the negative. So it simply means that the current on this 4 ohm resistor is going downwards. That means it's having V1 and it's still V1. Then on this other side, so it's now, since it's the same node, the voltage is the same. But it simply means now that all I'm going to be considering is now the direction of current. So this is positive, it enters through the positive and leaves through the negative, so it's going down. So if that be the case, this is the same thing as saying current, whenever I have a voltage up and a voltage down, and I have let's put it this way, whenever I have a resistor in between two voltages up and down, what it simply means is that whatever voltage I have up and the one I have down is going to be subtracted from it, it will be equals to the given voltage that is in between, and the given voltage in between is just 10 voltage. And notice that this is V1 up here, and what is down here, we always choose a reference point. So let's say we choose this reference point to be ground. The voltage on ground is always 0, so V1 on this ground is 0, while V1 here is just V1. So it simply means if I'm talking about V1 minus 0, and V1 is V1, so it simply means the same thing as saying V1 minus V1 is just going to give me 0, equals to 10V. This is the same thing as saying 10V is equals to 0. On this second part, applying the same principle, this particular node, this is a node, this is a node, all this gives me just one node. That's why I call it V1. As we use the example that involves more than one node, it will become clear. So this on this end, this is going to be the setting as V1 minus the ground, and this is also V1 that is here, equals to what is in between is 12 volts. So this is 0 equals to 12 volts, which means that 12 volts is equals to 0. So I just want you, why I'm putting this, normally you can overlook this principle, but why I'm putting this principle is so that by the time you're reading, you always remember that whenever you have a voltage up and a voltage down and a voltage in between, the voltage up will subtract the voltage down and it will be equals to the in between voltage. So if I've noted that, let's now go to the currents. Remembering that Ohm gave us V equals to IR, that is the work done in moving a charge through a metallic conductor, is equals to the output, which is current. That is proportional to the output, which is current. So we have this resistance is the proportionality constant. So if I know that the current here, let's say I call this one I1 and I call this I2. The current on I1 will simply be the setting as say using Kirchhoff's law, sum up all the currents here. If this is the node, this is node, this current is going down here, this one is going down here, so it's going to the node, it's entering this node, this is entering this node, this is entering this node, there is nothing living here, it's entering the ground, and the ground is the center with what is up. So you do I1 plus I2 equals to 0. That is Kirchhoff's law. Sum of current entering equals to the what is leaving, or you say the total current equals to 0, net current equals to 0. So if that is the case, the current I1 here is simply V1. This is, remember how to find currents in nodal analysis. We normally do whatever current you have, the same way we did voltage, is equals to, you get the current by saying, if I go to Ohm's law, remember that I is equals to V over R. Now, when you have to do it in nodal analysis, how to find the current is simply saying the difference in voltage all over the resistor in between. Notice that this is V1 up here and this is V1 down here. You see this? Now, and we remember that when we did this initially, we said that V is equals to V1 here and V1 here is equals to 0, and that 0 is equals to the 10V that is in between. So it simply means that what I will now be looking at is simply saying 10V that is here all over the 4 ohm resistor. Remember this. So normally, assuming this is different, maybe V1 and V2, I could have just had V1 minus V2 all over 4. But since V1 and V1 is the same and it gave us equals to 10, 0 equals to 10, that means 10 equals to 0. So we replace it. So we have 10V over 4, then plus for I2, the same thing. So it's going to be 6 all over, or what am I doing? It's going to be 12 all over 6 equals to 0. So the current here equals to 0. So this is going to give me 2.5, and I've told you the voltage is the V, will normally write, it doesn't matter. 2.5 plus 2 is equals to 0. That is the total current equals to 0. So this is going to be the same thing as saying, and this is going to be the same thing as saying 4.5 amps equals to 0. That is equals to total current. But I don't want you to just call this 0. Remember that since this is moving this way to the ground, it's leaving coming here, and that means if this is going from here this way, it's more like saying everything here will be going this way and everything here will also be going this way. So that means that our IN, that 10 ohm resistor we removed, we short circuited, is going this way. So if that be the case, the combination of these two currents, because this is the whole current inside this node, is just a node. The total current in this node is 4.5. That means it is equals to our IN. That is the Newton's current. So finding current in the 10 ohm resistor is simply going to be just this. And once we've gotten this, we can now apply the final rule of Norton, which is putting the current, the resistor, and putting the current, the resistor, the load resistor, and then the Norton's currents in parallel. So let's analyze this so you see what I'm talking about. So now that I've gotten 4.5, all I'll just do is to come and say, using that principle of Newton, we now have a current that will be here, the total current, which is, that is IN equals to 4.5, then yes. Now that I've gotten Norton's current, I'll put the load resistor RL, which is 10 ohm. This is the load resistor. But then I need to find the Norton resistance, and Norton resistance is the same thing as Thevenin resistance. So if I'm to find the Thevenin resistance, all I need to do is to come back to this particular circuit. I'm coming so that I will complete it. So the next one that will be here is the Rn, Norton's resistance. So I will come back to this. So we've gotten what they asked us to find in this question, but I'm just trying to show you the completion so you see what Norton's theorem is all about in full. So let's say I come here and come and do the whole resistor as I have this. Okay, let me use it this way. Let's do it this way. If I have this, the circuit, you will remove every voltage. So all the voltage here will be short circuited. Or should I? Yes. So this voltage, remove it. This voltage here, remove it. So just the resistor. So 4 ohm, 6 ohm. So that part where you have that 10 ohm resistor, the 10 ohm resistor was here or is here. So all you just need to do is to open circuits, give it an open circuit. So it becomes an open circuit. This is how you go about finding the RTH. And RTH is the same as Norton's resistance as well. So if I want to now find this, I'll be looking from here now, looking at this. From here, looking at this. You see that if I decide to look at this way, run this way. Yes. So looking at this way, you see that these two are actually in parallel, not in series. Because watch, assuming is something here and here, that will be series. But here you will now see that this will look at this, and then this will look at this. So using parallel is simply the same thing as saying arrow equivalent, that is the total current, will be the same thing as saying 4, that's our rule, 4 times 6 all over 4 plus 6, and this is going to give me if I do 24, over 10. Yes, over 10, which is going to be the same thing as saying 2.4 ohms. So the Rn here is going to be 2.4 ohms. So this is the Norton's circuit for this. This is how it should be.